Shown in the figure below is an electrical circuit. The values of the components are as follows. R1 is 1 kilo ohm, R2 is 2 kilo ohm, R3 is 3, and the two voltages V1 is 10 volt and V2 is 20 volt. We are to use Kirchhoff's law to solve for everything in this problem. In using Kirchhoff's law, we'll be writing both loop equations as well as junction equations. To facilitate this process, we begin by identifying the two junctions in this circuit, indicated by the two green dots. Only at junctions do the values of the currents change. Therefore, any one current goes from junction to junction. And we're going to arbitrarily label our three currents as follows. Going from the bottom junction to the top junction through the first battery and resistor R1, we're going to call that current I1. Going down through the second resistor, we're going to call that current I2. And finally, going around through the second battery and the third resistor, we'll call that current I3. In writing these three currents, I absolutely care less about which direction I draw the arrows. At the end of the day, the mathematics will give me a combination of positive numbers and negative numbers for the three currents, I1, I2, I3, and a negative value simply means that the current flows in the opposite direction as the arrow. The arrow is a convention. It does not have to be drawn in the direction of the final answer. That's actually a really good thing because in many Kirchhoff problems, you just can't tell what's going to be the direction of the final answer. We'll begin our Kirchhoff analysis by writing two loop equations. There are three reasonable loops that could be followed in this problem. The small loop on the left, the small loop on the right, and a loop around the perimeter. We're going to choose first to do the small loop on the left, beginning in the lower left-hand corner indicated by the red dot. We will first cross the battery V1, and as we cross the battery V1, we recognize that we are climbing uphill because we're going from its negative to its positive terminal. Therefore, uphill is a positive change in voltage, and we'll get plus 10 volts for that contribution. Next, we'll cross the resistor R1, which is 1 kilo ohm. The voltage drop across any resistor is that V is equal to IR, so we're going to get 1 kilo ohm times a current. And the operative question is whether we are going uphill or downhill. Current in an electrical circuit, just like water in a stream, always flows downhill. If we are moving with the current, we're going downhill. If we're moving against the current, we're going uphill. Looking at the way we have labeled the diagram here, we recognize that I1 is flowing from left to right through resistor R1. Since that is the same direction in which we are taking our walk, we are moving with the current, therefore we are flowing downhill, and we will have minus 1 kilo ohm times R1. That term as drawn is completely correct. However, we can choose to simplify a problem. Typical circuits that you encounter do not really contain resistors of 1, 2, or 3 ohms, and typical circuits do not contain currents of 1, 2, or 3 amps. More often, as is true for this circuit, we will find that kilo ohms are typical resistances and milliamps are typical currents. However, if we look closely at Gauss' law, since V equals IR, if we were to express our currents in milliamps and our resistances in kilo ohms, kilo times milli cancels one another. And so we can choose a convention in which all R's are kilo ohms, all I's are milliamps, and get the correct solution. One does not have to choose this convention, but we find it here to be convenient, and that will make our algebra simpler. For that reason, R times I is 1 kilo ohm times I1. Finally, to complete the first loop, we will continue going through R2. Since we are moving with the current, we will get negative 2 kilo ohms times I2 because we're moving downhill. Whenever you return to the beginning point, the total change in voltage must be 0, and so these three terms sum to 0. Now that we've drawn one loop equation, we need to decide whether it is appropriate to draw another. The rule of thumb is this. Any new loop equation must use at least one circuit element that has never been used before. We notice that the voltage V2 and the resistor R3 have not yet been used in a loop equation. Therefore, our next loop should include at least one of these elements, and it will, since we're going to start at the red dot, and from the red dot we're going to choose a path which is clockwise along the right-hand small loop. In this case, the first circuit element that we cross will be the resistor R2. Since we will be traveling against the current, that means we're going uphill, and therefore we will get positive 2 kiloohms times I2. We next cross R3, once again moving against the current. Against the current is uphill, so we will have a positive 3 kiloohms times the current I3. And finally, we cross the battery V2. For batteries, you don't look at the direction of the current. Instead, you look at which terminal you begin and which terminal you end at. In our case, we are starting from the positive terminal, going to the negative terminal. Therefore, we have dropped by 20 volts in crossing this battery. When we return to the beginning point, we have a total voltage change of 0, and this completes our second loop equation. Looking carefully at the circuit, we now find that each one of the circuit elements has been used in at least one loop equation. Therefore, it is no longer valid to write an additional loop equation because it will not be an independent equation compared to the ones we already have. We are left, therefore, in finding our third equation in three unknowns to reference the junction equation. And we're going to take the top junction. The junction equation says that the sum of the currents headed into any junction, in this case current I1 and I3 are headed into the junction, is equal to the sum of all currents leaving that junction. I2 is the current that leaves the junction, and this leads us to the third of our three equations in three unknowns. Having now formulated three equations in three unknowns, the only thing that lies between us and the final answer is a little bit of algebra. In class and in this video, I'm going to use the method known as Cramer's rule to solve this set of three equations. And Cramer's rule requires us to first begin by writing the equations in an organized manner so that the unknowns are in columns. I'll make the first column I1, the second column I2, and the third column I3. The expression that just appeared on the page is actually a rewriting of the junction equation in which I've moved I2 to the left-hand side of the equal sign. Rearranging the first of our two loop equations, we will have I1 plus twice I2 equals 10, and the last of our loop equations yields twice I2 plus 3I3 is equal to 20. Cramer's rule now allows us to write down in a single step the answer for each of the three unknowns, and we get this answer by taking a ratio of two determinants. The determinant in the denominator is the coefficients organized as shown in the three equations above. The coefficients in the numerator are similar except with one small change. The three numbers that are to the right of the equal sign in my well-organized series of equations will be used as replacements for the I1 column in the numerator's determinant. After these three have been placed, the rest of the determinant is simply a copy of the coefficients from the left-hand side of the equal sign. There are many tricks by which one remembers how to solve a 3x3 determinant. I'm going to use the one called writing the ghost determinant by writing a copy of the determinant to the right of the original. Now that we've written the ghost determinant, we'll be able to get the final answer simply by multiplying down diagonals. The first positive diagonal is here, yielding a value of 6. The second positive diagonal yields a value of 0. And the third positive diagonal yields a value of 2. Finally, we account for the three negative diagonals. Negative diagonal means that we subtract the product of the three numbers. We begin in the ghost determinant, and this diagonal gives us 0. This diagonal gives us -3, and so subtracting a -3 is like adding 3. And the last negative diagonal has a 0 in it, and so we get no contribution. We solve for the numerator in exactly the same way by writing the ghost determinant, following the three positive diagonals. The first positive diagonal gives no contribution because of the 0. The second positive diagonal also gives no contribution because of the 0. And the third positive diagonal has 1 times 10 times 2, which gives a contribution of 20. We complete the analysis by multiplying our way down the negative diagonals. The first negative diagonal makes no contribution whatsoever. The second negative diagonal, multiplying the three numbers, we get minus 30, but since it is a negative diagonal, we subtract the minus 30, which is like adding 30. Finally, the last negative diagonal gives us 2 times 20, which is 40. We must subtract this 40 from our calculation and get the final result for I1 of 10 over 11. We'll perform a similar calculation to find both the value of I2 and the value of I3. Since for each one of these Cramer's rule calculations, the denominator determinant is always the coefficients, that value is the same in each calculation whether it's I1 or I2 or I3, and we previously calculated the denominator to be 11. Thus, we only need to formulate the determinant in the numerator in order to get our final result for I2. In order to get the answer for I2, we replace the I2 column in the numerator determinant by the three values that were to the right of the equal sign in our well-organized equations. Those values were 0, 10, and 20, and then copy the rest of the determinant exactly as it normally appears in the denominator, 110 and 103. Again, we'll solve this determinant by writing the ghost and multiplying down the three positive diagonals and the three negative diagonals. The first positive diagonal gives us a product of 30, and so we will add a 30 into the numerator. The second positive diagonal multiplies to 0, and the third positive diagonal multiplies by 20, meaning that we will add a 20 to the numerator. Finally, we must complete the three negative diagonals. The first negative diagonal goes to 0, the second negative diagonal goes to 0, the third negative diagonal also goes to 0, and so in fact we have no calculations that are necessary in order to do the negative diagonals. Our answer is done, and our result for I2 is that I2 is 50 over 11. Finally, we perform exactly this same calculation in order to determine I3 as the ratio of two determinants. The denominator determinant, once again, is the same as the previous two calculations, and so we simply reuse the 11, but the numerator is going to take a little bit more work. Since we're solving for I3, the three values to the right side of the equal sign will be used in the I3 column. Those are the 0, the 10, and the 20. And the other two columns are copied from the normal determinant as 1, 1, 0 and minus 1, 2, 2. Once again, we solve the determinant by drawing the ghost. The first positive diagonal yields a value of 40, which we will put in the numerator. The second positive diagonal yields nothing, and the third positive diagonal also yields nothing. Thus, we move on to our negative diagonals. The first negative diagonal yields 20. 1 times 10 times 2 is 20, and we will need to therefore subtract this 20. The second negative diagonal yields negative 20, so we will need to subtract the negative 20, which is the same thing as adding 20, and the third negative diagonal gives us a result of 0, meaning that we have now completed the calculation for the current I3, and the current I3 is going to be 40 over 11 milliamps. Please remember that throughout this entire problem, we have decided to consider our resistors as kiloohms and our currents as milliamps. You could also solve this problem by considering your resistors in ohms and your currents in amps, and those results will be consistent with these. As a last step, it's actually a pretty good idea to take these three values and plug them back into the equations that you used to determine them to see if you got all the algebra right in between. The easiest of these three equations is the junction equation, which I'll copy here. I've put a question mark above the equal sign to indicate that I'm performing a test. I will plug in I1 and I3 on the left, and I'll ask whether it equals I2. Putting all three values in, we see that we're asking whether 10 10 over 11 plus 40 over 11 is equal to 50 over 11? And the answer is a resounding yes. This may seem like a quite thorough test, but if you think about it for a minute, there's nothing in this test that has actually exercised the denominator since we copied it 3 times. To do a more thorough test, let's call upon one of the other 2 equations, one of the loop equations, and I've arbitrarily selected this one. I1 plus twice I2 is 10. Let's find out if that's true. I1 is going to be 10 elevenths, and since I2 is 50 elevenths, we're going to double that to get 100 elevenths, and ask ourselves whether this gives us the value of 10. Well, 100 elevenths plus 10 elevenths is 110 elevenths, and if we simply do the division, we find that indeed these values satisfy the equation. Therefore, we conclude that our 3 values, I1, I2, and I3, written, as I remind you, in milliamps, are correct. The last part of this problem asks us to find the power dissipated by each resistor. There are several formulas by which we might calculate power. These are that P is VI, or eliminating V with Ohm's law, power is I squared R, or eliminating from the first formulation I with Ohm's law, power is V squared divided by R. At this stage in the calculation, we have calculated the current through every resistor, and so we know all the input variables to this formula. The other ones would require an extra calculation, and I don't want to do an extra calculation, so we will determine our 3 powers, power 1, power 2, and power 3, by using the I squared R formula. In this case, we're going to exercise a little bit of caution and put all of our variables back into MKS units. As you'll remember, the current I1 was 10 elevenths of a milliamp. Therefore, the current written in amperes is going to be 1/1000th of 10 elevenths, and that current should be squared. Whereas the resistor in this calculation is 1 kiloohm, and so we will write that as 1000 ohms, yielding a power of 8.3 times 10 to the minus 4 watts. We perform exactly the same calculations for power 2 and power 3 so that we can get the results: 0.041 watts and 0.039 watts. Each of these powers is low compared to the power dissipation capability of a typical off-the-shelf resistor, and so we expect that if we were to wire this circuit, it would not fry. And that completes our Kirchhoff analysis.